Hello. Today we're gonna tackle what is CUDA or Compute Unified Device Architecture. So CUDA is a C or C++ extension, or it's a language extension that what it does is through the extension of C and C++, you can express parallel computation. So what we're seeing here is a snippet of code that we can prove to execute very fast through parallelization. So what we're gonna do is matrix multiplication. First, let me explain what the program is doing. Suppose we have, see, okay. Suppose we have two matrix. Let's just say 3 by 3 matrix. So like space. So matrix like 3 by 3, and we have and this first matrix. Let's store it to the variable a. There. That's our first matrix. Our second matrix would be also 3 by 3, and we store it to B. Now we're going this program. What this program is going to do is it's going to multiply these two numbers. There's two matrices, and let's try to do that. The answer would be another matrix. Okay, and we're not going to tackle the how it does it. I mean the mathematics of this, like 3 and 1. But this is the answer. It's also another matrix. I'm sure there is a pattern how to do it, but this operation is inherently parallelizable. I mean, every cell of the matrix, like these and these, have been are computed independently, and then a final result is shown here. So if we go back to the program, the example here is it has 1,000 rows and 1,000 columns, and can see an array has been allocated as C++ is using the new function, and the result is also stored here. And you can see clock. Well, it doesn't even care what's the inside of the matrix, because after declaring them, matrix A and matrix B, it multiplies them right away. Doesn't even care what's the content of inside. Anyway, we just assume that there are random numbers in matrix A and matrix B. Just assume. And then multiply them A, B, result, and the dimension. And then prior to calling matrix multiply, It's taking the start time, and then it's taking the end times. Because this operation here, since it is 1000 by 1000, this is going to take some time to complete. Right? It's not going to, but it is parallelizable. Now, after it completes, this is usually how C++ it does it using the chrono steady clock uh, way, and you subtract the end and start. So you're gonna get the duration of how long it took. Okay, and then delete the memory. So this is the operation that is potentially going to take some time to complete. Now, this program is very small, but let us go to the definition of this function. It's as in the same file here. So it potentially has two definitions. This here or here. So its definition is going to be this one if the use CUDA preprocessor is not defined. So you'll see that it's doing it in a for loop for I equals 0 to rows A, for j equals 0 to rows B, and then, well, it just does the thing. It does the matrix multiplication. This is the first cell and second cell, multiply them, and this is the sum, and then put it into another cell in the result matrix. So since this is 1000 by 1000, so this is gonna be million, 1000 times 1000. Anyway, it's gonna be big. These are, I mean, three for loops. First for loop, an inner for loop, and another for loop. Okay, but this is how it does it. But what if the use CUDA preprocessor is defined? So this is gonna how it's gonna do it. Here, there's another definition of the function. So it's gonna delegate the operation in parallel. First, it allocates the matrix inside the in the GPU. So it does it using CUDA malloc, because right now this matrix A is in the system to the new in the RAM, but the CUDA malloc is allocating a memory not in the RAM but in the GPU itself inside the hardware. So you have to allocate the same size so as what is in the RAM. So this is what this tree CUDA malloc is doing here for the first matrix, for the second matrix, and for the result. Now after that, we have to copy what is from the RAM into the GPU using CUDA mem cpy. And these CUDA malloc and CUDA mem cpy are the Nvidia API. So they're implemented in a library of Nvidia. They're the CUDA API. So after copying, and you can see the direction of the copy here, host to device. Host is meaning CPU or system, and the device meaning it's the GPU or uh, the hardware graphical processing unit. And then this is uh, dem tree is like XYZ. It's like it's a structure with three members X, Y, and Z. But here we're defining the block size. So the way this works is each core of GPU has a block, and here it's 16 by 16, and then each block has threads. Could be the grid size. So just multiply that. For example, if there are um, maybe four threads per block, then 16 times 4 is so on. So that's the number of parallelization that is happening here. And then instead of doing a for loop, you are parallelizing the matrix multiplication part, the one that does the three nested for loops, is now calling the matrix multiply CUDA, which is just on top. Let's check that. And notice this opening and closing. And notice that in this opening and closing, we specify the grid size and the block size. This is how the number of parallelization. And this is matrix A, B in the result. But the interesting part here is the multiply coda here on top has the underscore global decorator. So the function matrix multiply coda has this decorator, uh, basically conveying the intention that the body of this function is now going to be invoked simultaneously inside a GPU. So I'm saying simultaneously, so I'm saying 10,000 simultaneous, 100,000, something like that, based on the grid size and the block size here, based on this opening and closing. So that's how many are these function here invoked at the same time. So this if here is just to protect from accessing outside of the bounds of the array, but this is really not needed. It's just for protection to make sure that we're not accessing outside of the array, that the I is within the rows and the J is within the columns. And the sum, notice also that we only have one for loop here. And then the result is that this part here is the same as the previous part, except that instead of having two for loops, this one only is having the inner for loop here. So it's only having this last for loop, this one. And what happens is that the outer for loops is now Coda is now the one responsible for that. So because there will be simultaneous reentrant calls inside this function, okay? So this the block the function I'm highlighting here will be invoked in parallel. That will be simulating the first for loop, these two for loops here. But instead of being sequentially invoked, it's doing that in parallel. That's the essence of Coda. So yeah, you have to be careful how to structure a code. Make sure that this part here indeed is co-independent of each other, like it does not depend on other calculations of the cell. So if you try to check the access of the matrix I and K is being differentiated by calculation here using this variable, the block, and the thread IDX, making sure that I and J is different is for each call here so that they are parallel. in parallel. So for the first call, I and J would be different, and then this one will be accessing a portion of the array. Another second call at the same time of the first call will have a different value of I and J, and so on. So they are mutually independent of each other, as they are to be calculated in parallel, and that makes the CUDA very fast. But how fast? Now let's see. Of course, you have to include this header file here, the CUDA runtime. Now the make file here is looks like this. Okay, so when we build this, we specify if the coda use coda is 1, then we're gonna use define this variable as use coda. Otherwise, this is going to be no coda. It's going to be either use coda or no coda. Okay, and if we look at the code here, see, it's using this preprocessor, use coda or anything else. So this is what is intention here. This is going to be pre-processing, the preprocessor part. Notice also the compiler that we're going to use is NVCC, because the opening and closing bracket is not a C++ thing. So this part here, where's it? Opening and closing. This is not a C++ keyword or operator. I mean, we can create an operator like this using C++ template, but even in C, it's going to be like this. Okay, because CUDA can be called in C, and this is actually an extension to the C language. So it's extending the C language. That is why it no longer compiles using GCC or any C compiler. That's why when we do CUDA, we have to use the CUDA compiler. And then through the call of the CUDA compiler, we have to tell it through the CCBin argument. Either it's G++ or GCC, depending on whether it's C++ or C. And then we have to pass this additional argument stuff, the compute capability, which is 5.3 in our case. Because every coder has a different compute capability bytecode. Here is 5.3. We can query this programmatically, the compute capability, or we can just use the hard-coded value. It's because it's well known for every GPU. And then the extension should be CU, because it won't compile if the extension is CPP or C. It should be CU. And then the rest are just standard GCC stuff. Include files and the library. It has to link to the coder runtime. I mean, if we open this file here, we have to link to the coder runtime. Here. So this is where we take our CUDA memcpy, CUDA malloc API. This is the CUDA API. Okay. But the opening and closing bracket is indeed extended C++. So we do the compilation, and it will produce an output matrix multiply. Let us do that now. So if I do make and do not specify anything, so it is building without coda. And if we run this and we time is execution, and this is how gonna it the, it's gonna take like um, to multiply 1000 by 1000 matrix. Okay, it's gonna take okay 14 seconds to complete. So it's gonna make clean. So it's gone, and then we're gonna make again. Use CUDA equals 1. So building with CUDA support this time. You can see the preprocessor macro is now defined, and once the preprocessor is defined, you can begin to see that the C++ code is going to use the other implementation of the matrix multiply, which now uses the parallelization. So we have an executable here, and then we run it again and see it only took zero point 0.5 seconds to compute the result. When CUDA is used, it's 14 seconds when CUDA is not used. So that is how fast is parallel programming CUDA. Very interesting concept in software engineering here. It's trying to combine hardware and software. This is what GPU